Hello, welcome to the Bakwas channel for self-paced tutorials on robotics. This presentation illustrates a few simple options to calibrate cameras for use in First Tech Challenge projects. Several robot operations, such as moving to a location or recognizing objects, require a consistent degree of accuracy from vision data. The acquired images have to be rectified such that calculations using image data are rendered as hardware independent for use in OpModes. For this reason, cameras have to be calibrated not just to compensate for any lens distortion, but also for the resolution used to acquire the images. Calibration is essential for sharp and clear images. The images fed to the application should be camera neutral or agnostic in a broad sense. Without exposing the underlying math behind the calibration techniques, let us assume simply that cameras can provide usable images after basic calibration data are made available to the OpModes. The three methods to calibrate a camera are public domain software, commercial solutions, and custom programs that rely on popular graphics libraries such as OpenCV. There are excellent packages in the public domain to conduct camera calibration. The most advanced is MRCal from Jet Propulsion Lab, NASA. This package is beyond the scope of a simple introductory tutorial on camera calibration. The other packages on the slide have their advantages too. For example, Mobile Robot Programming Toolkit, MRPT, has Robot Operating System ROS 1 and 2 support with many examples. Given the fact that camera calibration is one minor feature in all these packages except for MRCal, it is best to keep an eye on the ball and stay focused on camera calibration solutions rather than getting carried away with the other features of these easily accessible programs. There is a detailed section in the MRCal documentation explaining the approaches to camera calibration. While it is helpful to browse the material to establish a better understanding of camera calibration techniques, usable parameters from camera calibration can be obtained more quickly with simpler techniques. The package provides a Python wrapper API for the principal C libraries. This slide displays the documentation from MRCal on how to run a calibration. Some of the topics elaborated are the calibration object, capturing the images, model choice, computing the coefficients, and interpreting the results. This tutorial will demonstrate similar activities with the other methods under consideration. The primary purpose in displaying this web page is to reassure that the processing steps are the same for all calibration techniques, irrespective of the complexity behind the scenes. "3DF Zephyr" is a photogrammetry solution that has a camera calibration option for beginners. There is a free version of 3DF Zephyr called 3DF Zephyr Free. This tutorial will illustrate this free solution shortly. Since 3DF Zephyr Free only needs the images to perform the camera calibration, it is a very practical choice for a rookie team in FTC projects. The issue is that it is limited to Windows platform only and requires OpenGL 2.0 driver support. Most FTC teams are on a tight budget. It does not make sense to evaluate other commercial solutions because camera calibration is a very small facet of these solutions. Why spend money on product whose major functions cannot be used for FTC projects when equally effective solutions are available at no cost? 3DF Zephyr has a camera calibration feature that is very simple to use. Simply load several images of the calibration target in slightly different angles and let the app perform the calculations of the calibration coefficients. The results can be exported to files to minimize transcription errors of long strings of floating point numbers. Custom solutions are generally made available by individuals, either through blogs or public repository as open source solutions. Obviously, the authors will stand on the shoulders of giants in the graphics industry to deliver a practical solution that can be tweaked by anyone with a passing interest in working with code. OpenCV has several camera calibration methods or functions. The authors of many custom solutions and commercial solutions generally provide some interfaces to capture the images and submit them to the many OpenCV functions for the number crunching exercises. These repositories cast a wide net in terms of programming languages, with C++ and Python as the two most dominant ones. The biggest advantage of these custom solutions is the fact that the ready availability of source code permits the solution to be ported to one's platform of choice. The key processing steps are: prepare the environment to perform the calibration. Collect images with the camera that is under calibration. Transfer the images to the environment where the calibration will occur. Conduct the calibration exercise. Examine the calibration coefficients. And finally, if there are errors below tolerance levels, then publish the data for use by the OpModes that require vision data. Otherwise, repeat the process from the second step. It is preferable to have the camera mounted on the robot and connected to the control hub. The FTC OpMode to capture images for calibration requires a gamepad that is attached to a port on the driver hub. The recommended test pattern is a checkerboard. The test pattern will require some nominal repositioning after each image capture. It is best to understand the range of movements for the test pattern that will constrain its position for the entire pattern to be visible to the camera during the image capture operations. While the FTC OpMode utility camera frame capture is the recommended software, it may be desirable to explore image capture operation functions by using one's own code for this purpose. This tutorial demonstrates in a later section a very simple Python script for this purpose. The FTC SDK has an example op mode called Utility Camera Frame Capture. Under Android Studio, copy this op mode to the team code section. Check two parameters, the resolution setting and the file name nomenclature for the captured images. The file names will have the prefix Vision Portal. For the supplied op mode, the file is written to the folder SD card on the control hub. Perform a cursory compilation build. The preferred target for the camera to acquire images for calibration is the classic checkerboard. One could use circles instead of squares, but there is lower accuracy for the calibration data when using circles. It may be prudent to obtain a commercially printed checkerboard test pattern if the budget permits. A monochrome print of the checkerboard will suffice if the scaling in X and Y axes are the same. For printing in-house on a standard inkjet or laser printer, ensure that no scaling is applied to the pattern. Also, ensure that no rasterization is performed by the printer driver. The printed pattern should be measured very carefully. Count the inner corners only. This checkerboard test pattern has 11 squares across and 8 squares down. The program uses only the inner corners of the squares for calibration. The parameter values are 9 by 6. This checkerboard test pattern has 8 squares across and 8 squares down. The program uses only the inner corners of the squares for calibration. The parameter values are 6 by 6. Before running the op mode, check the resolution setting in the code and make changes to the resolution values and nomenclature of the file name if necessary. The camera stream should be viewed so that the image has the pattern fully within the frame. The camera stream is accessible from the Cascade menu when three dots or ellipses are touched in the top right-hand corner of the window in the driver hub. Touching the camera stream window will refresh the image. After completing the review of the camera stream, touch the three dots or ellipses again and select Camera Stream to dismiss the camera stream window. The default button on the gamepad to capture an image is the square or X button. It is not possible to view the camera stream and to use the gamepad concurrently. The op mode utility camera frame capture will save the captured image to the folder /SD card on the control hub. All captured images have the prefix Vision Portal for the file name. Transfer the images to a folder that is accessible by 3DF Zephyr Free. If Android Studio is connected to the control hub, then its Device File Explorer window pane can be used to transfer the captured images with standard drag and drop operations, especially if you are in a Windows environment. Start the control hub and the driver hub. On the driver hub, launch the driver station app. Check that the robot is connected and the network is correctly identified with the gamepad attached on user 1. Make sure that the battery levels are correct for both the driver station and the control hub. Go to the teleop menu, select camera frame capture, and select the Init button. Then go to the top right-hand corner, click on the three ellipses and look at the camera stream. If the image is positioned appropriately, you can dismiss it by clicking on the three ellipses again and selecting camera stream. Now touch the play button and start collecting the images by using the square or X button on the gamepad. Capture approximately a dozen images by pressing the square button to capture the current image and then moving quickly to change the position of the checkerboard slightly for the next image. Repeat the capture and checkerboard change in position successively. The entire checkerboard must remain in full view of the camera. Avoid moving the checkerboard when pressing the square button. After the desired number of images have been captured, stop the op mode by pressing the stop button. Here are some sample images that were captured and will now be used in the calibration process. The captured image files need to be transferred for use by the calibration app. The image files are in the /SD card folder of the control hub. The common prefix for the files is Vision Portal. Use Device File Explorer in Android Studio to transfer the files to a subfolder that can be accessed by the calibration app. Naturally, there are other methods to transfer the files from the control hub to a working folder. Launch the calibration app. Drill down to the calibration section. Select the images files. Let the app crunch the numbers to display the results. Export each set of coefficients as a calibration file for use in OpModes as necessary. Here is the example of a custom Python solution to capture the images, calculate the coefficients, and then test the coefficients. Three separate Python programs. Let's look at the first one, which is shown here as image acquisition. And basically what we're doing is making sure that we're using the correct resolution to capture the images and relying on OpenCV to collect the image and to save it onto a folder in the system. The next program is calc coefficients, and again we rely on the libraries in OpenCV to do the calculations for the calibration. We're using a chessboard pattern, the same one that we used for the standard OpMode method, and we allow the user to iterate through the number of frames that they want to collect. The advantage in this solution is that the user can see the frame before they select it for capture. The final Python program is test calculations. We take the data that calc coefficients produces, plug it into this module, and then see whether the calculations stand up to the litmus test. If you need more information on these Python programs, please do let me know. Launch 3df Zephyr free. Drill down from the main menu bar, select Add Images button. Use the File dialog box to open the image files. Perform the calibration. Note the estimated calibration values and export the values for use in FTC projects. This is where the rubber meets the road. Transfer the calibration results to a basic OpMode for validation. This can be done either by updating the resource file team webcam calibrations.xml or passing the coefficients as parameters in your OpMode. This slide illustrates the typical entries for the calibrated camera data. Note the structure of the XML file whose root tag is calibrations, that is plural. Calibrations may have one or more camera entries. Each camera is uniquely identified by the vendor ID, VID, and the product ID, PID. Each camera entry will have one calibration entry corresponding to a resolution setting that will be used in the OpModes. The other attributes are focal length, principal point, and distortion coefficients. Naturally, if one is planning to use a camera at several resolutions, there will be several calibration entries. This data can be passed along by the OpMode to the Vision portal during runtime. This tutorial introduced camera calibration for First Tech Challenge robots. The FTC SDK has an example OpMode to capture images. This OpMode and a standalone Python script were demonstrated for the acquisition of images from the camera that is undergoing calibration. The captured images were processed by 3DF Zephyr free camera calibration feature as well as a standalone Python script to compare the data. The calculations were published for use within team code OpModes for FTC robots. This presentation was limited in scope intentionally to ensure that viewers get started on the practical exercises without information overload. That's all, folks. Please provide feedback in any which way you can. This presentation was prepared with assistance from resources as noted on the slide. My apologies if I have unintentionally or inadvertently omitted anyone or any resource. A very big thank you to y'all. Come back to the channel soon.